We're finally here. Today we will start with a topic that is purely probability and definitely differentiates the subject from analysis: conditioning and independence. We're only going to start very briefly with the notion of conditional probability. We'll come back to it later in much greater detail. Given a probability space and an event in that probability space that has positive probability, we can construct a new measure called the conditional probability relative to that event B. It's defined on the same sigma field, and it is defined as follows. The probability of A given B is the probability of A intersect B divided by the probability of B. It's not at all hard to check that this is a genuine probability measure. In fact, doing so was essentially on your first homework assignment. What does it mean? Well, our probability space models some experiment, and in this experiment, we're looking at the likelihood of different events occurring. Those likelihoods are determined by certain experimental setups. As we conduct the experiment, we might get new information that a certain event B is no longer in question. It has occurred. And so now we want to know what are the probabilities of other events given that information. Some of them might not be affected, others might be affected greatly. This conditional probability is a model for that. For all events, it tells us what is their probability given that we now know that the event B occurred. Let's look at our favorite example in terms of tossing a coin. If we toss a fair coin twice, our standard model is the sample space consisting of these four outcomes: heads, 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 tails, tails, heads, and tails, tails. Since it's finite, there's no technical obstruction to taking the sigma field to be all subsets, and as usual, we have the uniform probability measure. Any one of those four outcomes is equally likely. Now let's look at a particular conditional probability. What is the probability that the second toss is heads, given that the first toss was heads? Does the first toss being heads give us any information about how likely it is for the second one to be heads? If you've ever gambled in a casino, you will have a gut feeling that the answer to this is yes, absolutely. But you might not agree which way it goes. You might believe that there are winning streaks, and so this makes the second heads more likely. You might believe, on the contrary, that having more heads in a row is less and less likely, and so if I've had a bunch of heads in a row, the next toss is less likely to be heads. Let's actually do the calculation. By definition, this is the probability of the intersection of the two events divided by the probability of the second event. Well, what is the first event? The event that the second toss is heads consists of these two outcomes. And the second event that the first toss was heads consists of these two outcomes. Now, that intersection in the numerator has just one outcome in it, heads, heads. So this is the probability of the singleton, heads, heads, divided by the probability of the two outcome event, heads, 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 tails. The top has probability 1/4, the bottom has probability 1/2, and so we get 1/2 as the conditional probability that the second toss is heads, given that the first was heads. Now, notice that that 1/2 is exactly the same as the probability that the second toss is heads, full stop. After all, this event is just the two outcome event, heads, heads, tails, heads. So what we see here is that the probability of A given B, in this case, where this is the event A and this is the event B, is just the same as the probability of the event A. The likelihood that A occurs didn't change when we were given information that B occurred. Using the definition that this is the probability of A intersect B divided by the probability of B, we can rewrite this outcome as the probability of A intersect B equals the probability of A times the probability of B. That's a nice way to write it that doesn't actually rely on the event B having positive probability. And so we see that in this case, these two events are statistically independent. The likelihood of one of them occurring does not change when given information about the other. So that's our formal definition. Two events in a probability space are called statistically independent if the probability of their intersection is the product of their probabilities. This makes sense even if one or both of them have probability 0. But notice that in the case where the probability of B is positive, we can then divide by the probability of B and see that this is equivalent to the conditional probability of A given B is the same as the probability of A. Similarly, if the probability of A is non-zero, then this is equivalent to the conditional probability of B given A being the same as just the probability of B. There's a nice symmetry here. If A and B are independent, then B and A are independent. Now, more generally, we'll talk about classes of events being independent. If I have two sets of events, C1 and C2, in the sigma field, we call them independent if, given any event from the first class and any event from the second class, those two are independent. It will be useful and customary to apply this usually when those classes are sigma fields, although that won't always be the case a priori. We will soon see that we can usually boost independence from classes to sigma fields under reasonable conditions. We could make the definition just for sigma fields of events if we note that we can recover the original definition by saying that two events, A1 and A2, are independent if and only if the sigma fields they generate are independent. That might sound like a stronger property, but let's note that for a single event, the sigma field that it generates has four elements: the empty set, the event itself, its complement, and the entire space. That is, at most, four elements. If A is either the whole space or the empty set, this will only have two elements. The observation from that is that if A and B are independent in this sense, then they're also independent in the sense that their sigma fields are independent. And why is that? Well, we just need to check that all four elements here on both sides for A and B satisfy the independence criterion. So let's just check that. Let's hold A fixed and vary elements of the sigma field generated by B. The probability of A intersect the whole sample space, well, A intersect the whole sample space is just A, so that's the probability of A, which is the same as the probability of A times 1, which is the probability of A times the probability of the whole sample space. Therefore, the sample space is always independent from everything. Now, our assumption was that A and B are independent. What about A and B complement? Well, we can just draw a little picture here. If this is B and this is A, then A intersect B complement is this over here, which is the same thing as A minus the intersection of A and B. So that's the same as the probability of A minus A intersect B. And so since P is finitely additive, this is the same as the probability of A minus the probability of A intersect B. Our assumption is that A and B are independent as events, and so the probability of A intersect B is the probability of A times the probability of B. And so this factors as the probability of A times 1 minus the probability of B, which is the same thing as the probability of A times the probability of B complement. And therefore, if A and B are independent, so are A and B complement. In particular, putting these two together shows us that A and the empty set are independent, since the empty set is the complement of the whole space. And now we can run through the same, holding B fixed and varying A if we like, but we'll get the same result. So independence has nice functorial properties transferring to sigma fields, at least the sigma field generated by a single event. In a few minutes, we'll see how we can generalize this to sigma fields generated by larger classes under the right conditions. But first, let's talk about independence of more than two events or classes. What should it mean for three events, A, B, and C, to be independent? One possibility is to just declare that it means pairwise independence, that any two of them are independent from each other using the notion we already developed. So let's look at an example of pairwise independence. Let's take two fair coin tosses again and consider the following three events. The first event is that the first toss is ahead, like before. The event B is that the second toss is ahead. And the third event, C, is that the two tosses are different from each other. So we can just write down in terms of the sample space that we have what those events are. Each of them have exactly two elements. That means that each of them has probability 1/2, and therefore the product of the probability of any two of them is 1/4. Now we just need to check, what are those intersections? Well, A intersect B is the event that the first and second tosses are both heads. So that's only one event. That's the probability of heads, which we know is 1/4, which matches this. And that means those two are independent. How about A intersect C? That's the event that the first toss is heads and the two tosses don't agree, which means that the second toss is tails. And so this is the probability of the single event heads-tails, which again is 1/4. Good. And B intersect C is the event that the second toss is heads and the two don't agree, therefore the first is tails. So this is the probability of the singleton tails-heads, which is also 1/4. And we see that these three events, A, B, and C, are pairwise independent. But if independence is going to have any actual philosophical meaning, these three events cannot be considered independent. Because if I know that A and B both occur, then I know with absolute certainty that C does not. A and B together mean heads, which means that C cannot happen. Therefore, those three events should not be considered independent. So this pairwise independence is not going to be the right notion of independence that we want. Now, if we want to use the set theory symbols that we've been working with so far, this implication that A and B implies the negation of C, we could write simply as the intersection of A and B is contained in C complement. In other words, A intersect B intersect C is the empty set, which means that it has probability 0. Now, on the other hand, furthering the pattern of what we saw statistical independence means, if we take the product of the probabilities of all three of those events, that's 1/8, which is not 0. And so that's one numerical way that we could define independence that would show us why this set of three events is pairwise independent, but not independent. But we need to be careful. We might just want to say independence of three events means that the probability of their intersection is the product of their probabilities. But that is weaker than what we had before. That does not imply pairwise independence. For example, suppose that we just take C to be the empty set, and A and B be any two events. Well then, this is 0, and the intersection here is empty, and therefore this is also 0, so we do get agreement of this triple product. But we could certainly arrange it so that A and B are not independent from each other, so that the probability of A intersect B is not probability of A times probability of B. For example, we could take A equal to B to be an event that has probability neither 0 nor 1, and then this would show that the triple product does not imply pairwise independence. If you'd like, you can think up more interesting counterexamples as well, where none of the three are the empty set. Those actually play an interesting role in hashing problems in computer science, but that's outside the scope of this course. So we want a definition of independence for multiple events that is robust. And in fact, it makes sense to flip the script here and define independence for classes of events, specializing to individual events afterward. So suppose I have n classes of events, C1 through Cn, in a sigma field. We call them independent if, for any subset of the indices 1 through n, that's what this notation means, by the way, square brackets n is the set from 1 up to n, the probability of the intersection of events AI taken with indices in the set capital I is the product of the probabilities of those events for any choices of events AI in class Ci. That's a bit of a mouthful. Let's look at an example with n equal to 3. With n equal to 3, let's look at all subsets of the set 1, 2, 3. There are, of course, 8 of them. If we take the empty set, then the statement here is vacuous. If we take the 3 one-element sets, then those are just the statements that the probability of AI is equal to the probability of AI, which is automatic, so we never need to consider that. How about the 2-element sets? Those are the probability of AI intersect AJ, where I is not equal to J. And the statement is that those all have to be the probability of AI times the probability of AJ in those cases. In other words, the 2-element sets give us pairwise independence. And then the 1 3-element set gives us that the probability of A1, A2, A3 intersected is equal to the probability of A1 times the probability of A2 times the probability of A3. So this condition here gives us all of the double, triple, quadruple, etc. comparisons that we need together to mean independence. Now, I want to show you what's more or less a notational trick, but that makes this a little easier to digest at the level of classes of events, which is to say, from this definition, if I have a finite set of classes that are independent, then I can throw in the whole sample space to each class, and those will also be independent. The proof of that is just like we saw on the previous slide, because the whole sample space is independent from everything. But having that in place makes the notation a whole lot easier here. Because, for example, if I had n equal to 5, here's one of the 3-element subsets we need to consider. A1 intersect A3 intersect A4. But I could just write that as A1 intersect the whole sample space, intersect A3, intersect A4, intersect the whole sample space. And indeed, the probability of A1 intersect A3 intersect A4, which for independence to hold is supposed to equal the probability of A1 times the probability of A3 times the probability of A4, is also equal to the probability of A1 times the probability of the whole sample space times the probability of A3 times the probability of A4 times the probability of the whole sample space. And so allowing the events AI to include elements of the class Ci and the whole sample space, in other words, by including the sample space in Ci, we can restate independence as just requiring that if I have classes C1 through Cn that, without loss of generality now, we'll assume include the whole sample space, they are independent if and only if the probability of the intersection of A1 through An is the product of 1 through n, the probability of Ai, for all choices of Ai in Ci, because Ci includes the whole sample space. That's a compelling reason to always, without loss of generality, assume that our classes include the whole sample space. Now, like before, if we want to talk about independence of n events, we would say that n events are independent if and only if the sigma fields that each of those n singleton events generate are independent. Those sigma fields each include the whole sample space by definition, and so that fits this definition right here. But it does, of course, include all of these conditions